Hi everybody, welcome back. This is example 10.6 and we are in the middle of our momentum chapter, and we're talking about, in particular right now, we're going to be talking about inelastic collisions. Inelastic. And this means collisions of two objects that either stick together in some way or there is some loss of energy. If we think about an elastic collision, you think about something like, say a super ball that bounces off a concrete floor and bounces almost all the way back up to the height it came from. Or if you think about elastic, you think about those ball bearings in those Newton's cradle toys, where the ball bearings transfer momentum and energy just about perfectly. But in an inelastic collision, like the one we're going to look at, we have conservation of momentum. This is definitely in play. That definitely works. But is energy conserved? Conservation of energy. Well, the energy that we care about, especially kinetic energy, we're going to find that is not conserved. Because we have two football players, and they're running different directions towards each other. We have our running back right here, and we have our linebacker right here. And we're going to find that their momentum is definitely conserved. So our initial momentum, initial momentum of the running back plus the initial momentum of the linebacker is going to be equal to the final momentum of the running back and linebacker together. But the kinetic energy of the running back plus the kinetic energy of the linebacker, final kinetic energy of the running back and linebacker, we're going to find that that is not the case. If we add the energies of these two guys together before they hit each other, it's not going to be equal to what the final kinetic energy of them is together. I keep saying together, by the way, because what happens here is the two players stick together. Apparently in football, when you tackle another guy, you're supposed to wrap him up so he can't bounce off of you and keep going. So our linebacker is going to wrap up the running back right here, and they're going to fall to the ground together as one single unit. So we've got two parts to this question. Part A asks us, what is the final velocity of the running back and linebacker together? That is, which way are they going? They're running different directions now, but what's the velocity? And I should put an arrow over that because it's a vector. What's the final velocity of them together? And part B is going to be asking us, what's the initial kinetic energy of the whole system versus what's the final kinetic energy of the whole system? And these are going to be very different. So let's start with A, our final velocity of the linebacker and running back system. Let's start by writing down our knowns. We have a running back, and R is going to be my subscript for running back, and L will be linebacker. The mass of the running back is going to be 95 kilograms, and the initial velocity of the running back is 3.75 meters per second. Okay, the mass of our linebacker is 111 kilograms, and the initial velocity of the linebacker is 4.10 meters per second. But we need to add something to this. Remember, velocity is a vector. It's direction dependent. So if we say our running back, we'll just say that he's running in the positive direction, and that means our linebacker must be running in the negative direction. So he has a negative velocity. Let's make that a little smaller. There we go. Negative velocity for the linebacker. That's going to make all the difference. So we want to find out what the final velocity is of the running back and linebacker combination. Well, we know what the final mass, or we can find out very easily what the final mass of the linebacker and running. Oops, I did that backwards, didn't I? Running back and linebacker combination. That's going to be simply the mass of the one plus the mass of the other. Mass of running back plus mass of a linebacker. But this right here we can solve using the conservation of momentum. The fact that the momentum of the one player plus the momentum of the other player is going to equal the momentum of them both, whether they stick together or whether they don't. So let's write this out. The momentum, initial velocity of the running back plus the initial, did I say velocity? I meant momentum. The initial momentum of the linebacker is going to be equal to the final momentum of them together. We can break this down into their separate parts. We know that momentum is mass times velocity. So that's going to be mass of the running back times the velocity of the running back. Initial velocity of the running back plus the mass of the linebacker times the initial velocity of the linebacker equals the mass of them together times the velocity of them together. And that right there is really what we want to find. This is what we're solving for right here. So all we would need to do, it would appear, is simply divide by the mass of them together, which would give us mass of the running back velocity, running back, plus mass, what is that? Mass of the linebacker times the initial velocity of the linebacker. All that divided by, gosh, I can't draw a straight line. That's a little better. All that divided by mass of them together. That's going to equal the final velocity of the running back and linebacker together. Because, again, they're falling as one unit because the linebacker is wrapping the other guy up. So, let's simply calculate this out. The mass of the running back, that's 95. For the sake of, well, you know what? I should be a good example. I'm going to write my units in. 95 kilograms times initial velocity, that's 3.75 meters per second, plus the mass of the linebacker, 111 kilograms, times his initial velocity, negative 4.10 meters per second. All that over the mass of them both, their combined mass. So that would be mass of the running back, 95 kilograms, plus 111 kilograms. That should give us our final velocity of the two players together. 95 times 3.75 plus 111 times negative 4.10 divided by the combined mass. That should give us negative 0.48 meters per second as our velocity. This is the velocity of the running back linebacker system as they're falling to the ground together because they're wrapped up as one. So who won? Looks like the linebacker won, right? Because the whole system is going in the negative direction. Because it's going in the negative direction this way, and that means the linebacker must have driven back the running back. And that's how fast they're moving backwards together, or moving in his direction together. So that's part A. Come on now, there we go. That's part A. We have a final velocity of the two players together. But B asks us, what's the initial and final kinetic energies of the system? Initial and final. Well, we want to see if the kinetic energy of the running back plus the kinetic energy of the linebacker equals the kinetic energy of them together as they're both falling to the ground. And we're going to find out that they aren't equal. But let's find out what they are. So, initial kinetic energy. Initial kinetic energy is kinetic energy of the running back plus kinetic energy of the linebacker. final kinetic energy is simply the kinetic energy of the running back and linebacker system. So, initial kinetic energy. That's, well, what happened? Well, what do we do to find our kinetic energy of any one object? Well, we take 1/2 mv squared. So let's do that for the running back first. 1/2 mass of the running back times the velocity running back, or initial velocity, squared. There's an I in there. Okay, plus 1/2 times the mass of the linebacker. Mass of the linebacker times the initial velocity of the linebacker, that quantity squared as well. So that would be 1/2 times. Here's where, for the sake of space, I'm going to leave out units, but you should always write your units in. Mass is 95 times his velocity, that's 3.75 squared, plus, this is the linebacker now, 1/2 times mass of linebacker, 111 kilograms times his velocity, negative 4.10 squared. And we see, because that's squared, that negative is going to go away. Well, so why does direction not matter with energy? Kinetic energy is because kinetic energy is a scalar quantity. Think about it. Do you get less tired if you run north versus if you run south? No, you're expending energy either way. So kinetic energy is a scalar quantity versus momentum. We drew these arrows of the momentum right here because momentum is a vector quantity. But anyway, the point is that that negative goes away because the 4.10 is squared. So what's our initial kinetic energy of the whole system, the two guys added together? That should be 1,601 joules. That's a bad last line right there. Let's try that again. That's still really bad. My goodness. Last try. There we go. Okay, so that's our initial kinetic energy. Those two guys running together have lots of energy that's about to go somewhere. Okay, well, what's the final kinetic energy? Okay, final, that's simply the final kinetic energy of the running back and linebacker together. And we can solve for that. That equals 1/2 mass of, in fact, I'm going to make that a capital M, because it's the combined mass of the running back and linebacker together, times the velocity of them. Velocity of the running back and linebacker squared. Or I should really say the final velocity, which, by the way, we just found this out in the last part. This is that velocity right there. So let's plug that in. Equals 1/2 times their mass, that's 95 kilograms. There we go. Oops. Back up. I need to add that to 111 kilograms, right? Because it's the combined mass. Times their velocity. Well, we said their velocity at the end of the first problem was negative 0.48 meters per second. That value squared. So that's going to be the final kinetic energy of the system because they're both falling to the ground together. So what is it? What does that come out to be? It turns out to be 23.7 joules. The system's final kinetic energy is 23.7 joules. Very, very different from the initial kinetic energy of the system. These guys had a lot of energy going into this collision, but once they collide, that kinetic energy goes away. The energy does go somewhere, but it's not into the energy of motion. So is kinetic energy conserved? No, it's not. But is momentum conserved? Absolutely.